Hello students, welcome to this lecture on Wiener filter. Recall that Wiener filter assumes a linear filter structure for the estimator and estimates the filter coefficients by applying the MMSE principle. This is the signal model yn is equal to xn plus vn. Then it is passed through a linear filter to obtain the estimate x at n. And we have to determine the parameters of this linear filter. Given the random observations y n minus m plus 1, y n minus m plus 2 up to yn, then up to yn plus capital N, the Wiener filtering problem is to minimize the mean square error. This is the mean square error over all filter coefficient Hj, j going from minus n to m minus 1. This is the Wiener filtering problem. And the minimum is given by the Wiener-Hopf equation that we established in the last lecture. This is the relationship Rxyj, that is the cross correlation, is given by the convolution of the impulse response sequence, that is the filter coefficients, and the autocorrelation function. So, that way Rxyz is equal to summation Hi into R y j minus I going from minus n to m minus 1, and for j equal to minus n up to m minus 1. This lecture will examine the various interpretations of Wiener filter. It will discuss the FIR Wiener filter and the solution of the corresponding Wiener-Hopf equations. Let us interpret the optimality conditions for Wiener filter. The optimality condition for LMMSE formulation is given by this expected value of this error into yn minus j, that is equal to 0, for j is equal to minus n up to m minus 1. Thus, we can write, this is the error part, E of en into yn minus j is equal to 0 for j going from minus n to m minus 1. Now, this set of equations can be interpreted using our concepts of linear algebra of random variables. We showed that the random variables can be interpreted as vectors in a vector space. So, that those interpretations will help us. Recall the inner product space of real random variables, where the joint expectation Exy is the inner product operation. Exy defines an inner product. Random variables x and y are orthogonal if and only if E of xy is equal to 0. This is the definition. Now, the optimality equation E of en into yn minus j equal to 0 implies that the estimation error is orthogonal to each of the random observations. For example, E of n is orthogonal to y of n minus 1, etc. This principle of LMMSE estimation is called the orthogonality principle. That is, error is orthogonal to each of the observation random variable. Thus, En is orthogonal to each of the random samples yn minus j, j going from minus n to m minus 1. These random samples are linearly independent and spans a subspace W. All the random samples spans a subspace W. The error En is orthogonal to any member of this subspace. E of En into W will be equal to 0 for all W belonging to that subspace capital W. Thus, x at n, which is given by this expression, that is linear combination of y n minus I, is an orthogonal projection on the subspace spanned by the data vector. So, this is important observation. X hat n, that is the Wiener estimation, is an orthogonal projection on the subspace spanned by the data vectors. Let us try to have the geometric interpretation of orthogonality principle. Suppose we have to approximate a vector S as a scale version of another vector y. So, this is a vector y, this is vector x. We want to approximate x as the scale version of y, that is we have to find a y where a is a scalar. Now, if we draw up a perpendicular, then this part will be the orthogonal projection and this error will be minimum. So, the error E will be smallest when E is perpendicular to y. So, that is the orthogonality principle. So, we have to select this scalar multiple of y in such a way that error is orthogonal to the data vector. This is the orthogonality principle. Now, this orthogonality principle can be used to obtain the estimation error, because the minimum mean square error estimation error is given by this expression E of E square n. Then that we can write E of E n into E n, which can be expressed like this: x n minus summation h I y n minus I going from minus n to m minus 1. Now, note that this part is orthogonal to error. So, error is orthogonal to the estimate, this estimate. Therefore, this will be simply E of E n into x n. Now, if I expand this E n, that is x n minus summation h I y n minus I going from minus n to m minus 1, then we get this will be E of this expression into x n. And if I write now x n into x n, if we take the expected value, we will get R x of 0. Similarly, we will get the cross correlation function here by taking the expected values. So, that way E of E square n will be equal to R x of 0 minus summation h I R x y I going from minus n to m minus 1. So, the orthogonality principle can be used to derive the mean square error of estimation. We will interpret Wiener filter also as a correlation canceller. Observe that x n, that is the unknown signal, is the estimated signal plus error x hat n plus E n. Now, x hat n involves cross correlation between x and y n, and hence x hat n will be correlated with x n. E n is uncorrelated with y n because of the 0 mean and orthogonality. We know that E n is orthogonal to y n, but y n is 0 mean and consequently E n is also 0 mean. Therefore, orthogonal and 0 mean means that E n is uncorrelated with y n. So, this is very important, that E n is uncorrelated with y n. Therefore, LMMSE separates out a part of x n which is correlated with y n. Hence, the Wiener filter can also be interpreted as a correlation canceller. Whatever correlated part is there in the signal, that will be cancelled out. Now, question is whether the Wiener filter estimator is an optimum estimator. If x n and y n are jointly Gaussian, then the MMSE and the linear MMSE are equivalent, because that we have established in earlier lecture. Hence, the Wiener filter is optimum for the Gaussian case. Otherwise, we get a suboptimal filter, but it performs very well in applications like denoising, image restoration, etc. Though it is a suboptimal filter, because of its simplicity, it is very useful in practical applications. Now, we will discuss FIR Wiener filter. Consider an FIR filter of length m, characterized by the filter coefficients h0, h1 up to hm minus 1. There are m coefficients. So, that is a FIR filter of length m. The output of the filter to input yn is given by this relationship, convolution relationship, x at n is equal to summation hi yn minus I going from 0 to m minus 1. This is the filter output. And now we have to find out these filter coefficients. The filter coefficients are obtained by applying the orthogonality principle. What is that? Error is orthogonal to data. So, E of xn minus summation hi yn minus I going from 0 to m minus 1, that is the error, into y of n minus j will be equal to 0 for j is equal to 0, 1 up to m minus 1. So, this will give now the Wiener-Hoff equations, that is, if we take the expectation now, we will get summation I going from 0 to m minus 1 of hi into ry j minus I will be equal to rxy j, where j is equal to 0, 1 up to m minus 1. So, this set of equations are the m normal equations or Wiener-Hoff equations, and we have to solve these equations to find out the filter parameters. In the matrix form, we have RYH is equal to small rxy. This is the autocorrelation matrix of y, and this is the filter vector, this is the cross covariance vector. Thus, Ry is equal to this matrix Ry0, Ry1 etc. up to Ry m minus 1. Similarly, second row will be Ry1, Ry0 up to Ry m minus 2 and so on. Similarly, Rxy is the cross covariance vector and its elements are Rxy of 0, Rx of y of 1 and so on up to Rxy of m minus 1. And S is the vector representing the filter coefficients. There are m filter coefficients. So, these m filter coefficients are represented by this vector. We can find H by inverting this relationship RYH is equal to small r xy, therefore, H will be Ry inverse into small r xy vector. So, this inverse matrix we have to find out. Such direct inversion is not easy when m is large, because I know that Ry is an m by m matrix. So, if m is large, inversion will be very complicated. Now, let us examine this Ry matrix. We see that all its diagonal elements are Ry0. Similarly, these super diagonal elements will be Ry1, all elements will be Ry1. Similarly, this is also all elements along this subdiagonal will be also Ry1. So, that way Ry is a special type of matrix what is known as the symmetric Topliss matrix. Elements of each diagonal is same and elements of each super diagonal is same, like that elements of each subdiagonal will be also same. This is not only Topliss, but it is symmetric also. This one is Ry of 1, here also Ry of 1. So, that way this is a symmetric Topliss matrix, and this property is exploited to develop fast algorithm to compute H. We shall discuss one such algorithm in a later lecture. Now, this minimum mean square error of FIR filter, so that we have to find out. The minimum mean square estimation error is given by this expression E of E square n, that is E of E n into xn minus this estimate, and using the orthogonality principle as I shown earlier, it will be E of E n into xn. So, therefore, mean square estimation error is equal to E of E n into xn. Now, I can expand E n, that is xn minus summation hi into y n minus I going from 0 to m minus 1, and then multiplied by xn if we simplify, this will become Rx of 0 minus summation Hi into Rxy I going from 0 to m minus 1. This is the expression for mean square estimation error. The FIR Wiener filter can be realized as follows. We have the autocorrelation matrix Ry and the cross correlation vector Rxy as input to the Wiener filter estimator, and the estimator will compute the filter coefficients H0, H1 up to Hm minus 1. This is the input signal Yn. So, this input signal Yn will be multiplied by H0, then the delayed part will be multiplied by H1 and so on, and all these outputs will be summed up and we will get X hat n. So, this is the realization of FIR Wiener filter. Let us consider one example. This is a very important application, what is known as the active noise control. So, if we have to cancel the noise in a recording room, then this active noise control can be applied. Suppose we have the observation signal Yn, that is given by Yn is equal to 0.5 cos omega naught n plus phi plus V1 n. There is a noise in the signal where phi is uniformly distributed in the interval 0 to 2 pi and V1 n is equal to 0.6 Vn minus 1 plus Vn. So, this is known as a moving average model, MA1 noise. So, the signal Yn is a cosine function plus some noise. We want to control V1n with the help of another correlated noise V2n, which is given by V2n is equal to 0.8 Vn minus 1 plus Vn. This is the V2n. V2n and V1n are correlated noise. Now, using the two-step FIR Wiener filter, we will try to estimate V1n from this input, because they are correlated. Therefore, we can estimate V1 hat n here, and this V1 hat n, that estimated value, that will be added here. So, that it is positive and this is negative, and this part will be cancelled by this V1 hat n. This is the active noise control. So, that ultimately we will get the noise free part of this noisy signal. So, this is the filtering scheme, and we can find the Wiener-Hoff equations, that is given by R V2 into S, that is the autocorrelation matrix of V2 into S, is equal to cross correlation vector R V1 V2, where S is two length filter. So, that way it is S is equal to the vector composing of H0 and H1. Now, we can compute R V2 from the model, and these are given by 1.64, 0.8, 0.8, 1.64. This is the autocorrelation matrix of V2. And similarly, R V1 V2, this vector also we can compute from the model, and R V1 V2 is the vector comprising of 1.48 and 0.6. Therefore, we can find out now what will be H. H is equal to R V2 inverse into small r V1 V2. Okay. So, if we apply inverse this matrix and then multiply with this, and we will get this result, that is H0 is equal to 0.95 and H1 is equal to minus 0.976. So, now these are the filter coefficient corresponding to this two-step FIR filter, and when we filter this noise sequence with this filter, we will get V1 hat n, and this will cancel out V1 n. So, that way we get the noise cancelled output. Let us summarize the lecture. The Wiener filter optimality equations: E of En into yn minus j is equal to 0 for j going from minus n to m minus 1. These are the optimality equations. for the general Wiener filter we have considered, and these optimality conditions imply that the estimation error is orthogonal to each of the random observations. The estimator is an orthogonal projection of the signal on the subspace spanned by the random observations. Thus, the Wiener-Hopf equations can be obtained by applying the orthogonality principle. We have also seen that the LMMSE separates out that part of Xn which is correlated with Yn. Hence, the Wiener filter can be interpreted as a correlation canceller. The output of the FIR Wiener filter to input Yn is given by this, and these filter parameters or filter coefficients we have to find out using the orthogonality principle. Applying the orthogonality principle, we get the Wiener-Hopf equations like this: summation hi into Ry minus I going from 0 to m minus 1 is equal to Rxy j. For j is equal to 0 to m minus 1, m equations are there and there are m unknowns. Therefore, we can solve this set of equations to get the filter coefficients. In the matrix form, we have Ryh is equal to Rxy, that is autocorrelation matrix into H vector is equal to cross correlation vector. And we also observed that Ry is a symmetric top list matrix, and this property is exploited to develop fast algorithms to compute H. Thank you.